Today we're going to start talking about a special property of functions that kind of formalizes something that we've already made use of to a small degree. And this is the notion of continuity. So, what is continuity intuitively, and then we'll kind of get into what the precise definition is. Well, let's think back to some examples that we've seen where we have a certain nice property. If I'm dealing with a polynomial, let's say, or a rational function, or a bunch of other functions, as it turns out, but those are the ones that we've seen so far. One of the things that we proved by using the properties of limits, those limit laws that we came up with, we proved that if I want to find the limit of a polynomial, I don't even have to deal with the limits. I literally just have to evaluate the polynomial. In other words, the limit is found through evaluation. And the same is going to be true for a rational function, provided that the denominator isn't zero. In other words, we've got these functions and their limits are just found by evaluation rather than by having to do any kind of specific work to finding the limits themselves, okay? They're literally just evaluate the function. Well, that is the notion of continuity. We will say that a function is continuous if it has the property that we can find the limit by evaluating it. That's sort of our general notion of what it means to be continuous. Now, we need to make that precise, but first let's just kind of state that. So, find limits by evaluation. That would mean that a function is continuous. To make that precise, here's what we can say, and we need to be a little bit careful because you can find some limits by evaluation for certain functions, but not all of them. Like with a rational function, I can find the limits by evaluating, provided that we are not just, we don't have a denominator of zero. But even there's kind of a nice behavior for a lot of these functions where, well, they still do have some nice properties. So like the lack of being able to find the limit by evaluation isn't all that big a deal. However, the point is that it has the property at certain places. In fact, at most points, the rational function just fails to have this property at the points where it's undefined. So here's what we want to say. Being continuous isn't something that you either are or you aren't. We want to say that whether a function is continuous, whether it has this find the limits by evaluation property, depends also upon where in the domain we are looking. So what we are going to say is a function f is continuous at C if the following three conditions hold. Now, technically, the third condition kind of implies the first two, but we'll state them out explicitly just to make sure that it's clear. And then I'll say why kind of the third one implies the first two. So the first thing is f of c exists. That's important. The second is that the limit as x approaches c of f of x exists. And let's say that it is equal to some quantity L. Sorry, let's move that exists word over a bit so that it's clearer what's going on. And what do we mean by saying it exists? Well, remember how in the previous lecture we talked about these infinite limits and things, where we would write like, oh, the limit is equal to infinity or negative infinity, something like that. What we're trying to say here by saying that this exists is it exists as a real number. In other words, it's not simply that we say, oh, well, technically the limit doesn't exist as a real number, but we can express it as an infinite limit. No, we're saying this has to be an actual number as a limit. And the third thing is that f evaluated at c is actually equal to said limit. Now, really, if you just said f of c has to equal the limit, you could kind of say that's enough, in as much as, well, it's kind of complicated to kind of think about the technical things here, but the real gist of this is that evaluating has to equal the limit, and both of these things have to exist, okay? So in some sense, depending upon how you define this equality, this being true could be taken to imply that f of c exists and L exists. But we want to be careful. We want to make sure that nobody says, oh, well, what if both of them are infinite or something like that? That wouldn't make sense because a function cannot take on such a value. But then you could say, like, well, what if they're both undefined? Then two undefined things are equal or something. So we want to be careful to make sure that nobody gets confused that way. That's why we add in conditions 1 and 2, that both of these quantities exist as real numbers. So this property, this being continuous property, is really, really important because it tells us essentially that for these types of functions, we can find the limits through evaluation. Just to give some examples of continuous functions, polynomials are continuous on the entire real number line. Why is this true? Well, like I said, we proved, and I don't remember how many lectures ago it was, but we proved that for a polynomial, if you use the limit laws, you can show that the limit as x approaches a of p of x is always just equal to p of a. And this is true for any value of a. It's not just true at some specific point. Therefore, this is continuous everywhere. Why am I still wearing my mask? I was talking to people, and then I forgot to take this off when I started lecturing. I'm sorry. I'm just kind of scatterbrained or something about this. So, polynomials are continuous on the entire real number line. We can also say that rational functions are continuous on their domains. Now, one thing to notice, a function can only be continuous on its domain. It might not necessarily even be continuous on the entire domain, but it at most can be continuous on its domain because one of the requirements for continuity is, oh, this thing actually has to be defined at this point. Okay, so that is a very important part of this. This is as much as it could ever be continuous. Now, that's not to say that the limits are restricted to the domain. You can have limits at points outside of the domain, okay? That's perfectly fine, and we've seen that kind of thing before. For instance, the domain of x over x, this has a domain of x not being equal to 0, because if I plugged in x equals 0, I'd be dividing by 0. That's not allowed. Well, that's not defined. However, the limit as x approaches 0 of x over x, this is just equal to 1, and therefore the limit exists at a point outside the domain. So that's perfectly fine. But it's not continuous there because it cannot be evaluated at 0. So this is continuous on its domain. It's not continuous at 0, even though the limit exists. Now, other examples of functions that are continuous on their domains include exponential functions, which I'm for some reason having a great deal of trouble writing down. Exponential functions, these are going to be continuous on the entire real number line. By the way, an alternative notation for the set of real numbers is this. It's called a blackboard R. It looks like an R with an extra vertical line next to it. And yeah, we use this notation just to mean the set of all real numbers. So if you see this notation anywhere, that's what we mean. Similarly, people use blackboard Q to indicate the rationals, and they use blackboard N to indicate the natural numbers, and then if you remember back to complex numbers, they use a Blackboard C for complex numbers. So these are some just letters that we use by convention to indicate these sets. You don't have to use them, but they're actually pretty convenient to use because we actually talk about the set of all real numbers and things like that pretty frequently. If we have some nice, simple, one small symbol to indicate all the real numbers, yeah, that's great. That saves us some time when we're writing things down. All right, so exponential functions are continuous on the entire real number line. Logs are continuous on their domains. And let's see, trig functions. These are also continuous on their domains. Now, the fact that these are continuous is not necessarily obvious off the bat, okay? We have to be a bit careful to show that all of these things are continuous, but it turns out that they are. For instance, to show that the exponential functions are continuous, well, one way that we do this is essentially we use the fact that this is a monotonic function and it doesn't really jump around at all. And so you show that, well, for the rational numbers, it obeys our epsilon delta condition. And then when we move beyond the rational numbers, the way that we defined it was just by filling in the gaps. And it's a rather long technical proof that I'm not going to get into here because I don't think that it's particularly enlightening. If we were doing a full-on like senior level analysis course, then I'd be making you guys prove that these things are continuous, but we're not going to worry about that for now. So take my word for it on these, and if you want to read up more or hear more about why these are continuous, then let me know and I'm happy to help you out with that. Anyway, these are examples of continuous functions. So pretty much all the functions that we are used to dealing with are continuous on their entire domains. Absolute value of x, this is going to be continuous on its domain. And this one, we can actually verify is continuous on its domain. And I'm going to show you how you can verify that it is continuous on its domain. So how do we do this? Well, let's think about what is the absolute value of x. Now, the absolute value of x, I can think of this as a piecewise defined function. It's equal to negative x when x is less than 0, and it is equal to positive x when x is bigger than or equal to 0. So here's the thing. Let's think about the limit as x approaches a of absolute value of x. The first sort of situation to think about here is if a is less than 0, then this is the same as the limit as x approaches a of negative x, which is simply equal to negative a, which is the absolute value of a when a is a negative number. And therefore, whenever a is less than 0, this limit is equal to the absolute, the function itself. Because remember, the absolute value here, this is the function we're talking about. We're not simply thinking of this as some operation inside the function. This is literally the function that we are talking about. So in other words, what we proved is that if a is less than 0, then the limit exists and it's equal to the function at this point. And the function also exists at this point. Now, the same kind of thing happens if a is bigger than 0. In fact, it's even a little bit easier because then we have the limit as x approaches a of x itself. That's just equal to a, which is the absolute value of a for positive a. So verifying that it is continuous on each of those pieces is pretty easy. So this first bit, this shows us that we are continuous on the interval from -infinity up to 0, but not necessarily at 0. And this shows that I am continuous on 0 up to infinity. Again, not necessarily at 0. So at this point, I've shown that the absolute value is continuous everywhere except possibly at 0. And so that is the issue that we're going to have to deal with. What happens at 0? Well, we know that the function is defined at 0. Because the absolute value of 0 is just equal to 0. Okay, that's fairly straightforward. No, not anything too earth-shattering about that conclusion there, but let's move on and now talk about the limit here. So, how would I find the limit in this kind of a case? Well, the answer is, I have to think back to what we said, not so much in the previous lecture, but what we said last week about the one-sided limits. What I want to do is I want to take a look at the limit from the left and the limit from the right. Now, why do I want to do that? The reason I want to do that is because I know how to take each of those limits. So if I want to take the limit as x approaches 0 from the left of absolute value x, on the left-hand side of 0, this is just the function negative x. And so I can say this is the limit as x approaches 0 from the left of negative x. I can find that by evaluation because this is actually just a polynomial and it's 0. On the other hand, if I take the limit as x approaches 0 from the right absolute value of x, well, perhaps you've seen where I'm going with this, or perhaps you are seeing where I'm going with this, excuse me. Absolute value x to the right-hand side is just x itself. That I can also find, and it's 0. You put these two things together, so remember, for the limit to exist, the two one-sided limits have to exist, and they have to agree. But that's exactly what I just saw. So this means that the limit as x approaches 0, absolute value x, has to be equal to 0. Now, this means, if I put it together with the fact that the absolute value at 0 is 0, these two facts together mean that the absolute value of x is continuous at 0. However, we already showed it was continuous at all numbers except 0. So if it's continuous at 0 as well, that means that actually absolute value of x is continuous on the entire set of real numbers. And remember, this Blackboard R just means the set of all real numbers. So there we go. Now, this is maybe not the most complicated question. Maybe a lot of this might seem kind of in some way straightforward, but I like using these straightforward examples to start with, or at least the ones that don't have a lot of extra complication, because they can illustrate ideas that we're going to end up making use of later on in more complicated situations. So we're going to say a few more things about properties of continuity, but I want you to think about what we did in this piecewise defined function situation, because we are going to return to this kind of thing in a minute. When you're dealing with piecewise defined functions and you want to test for continuity, for where it's continuous, if you're talking about a point where near that point the function is just defined by one expression, then you just work with that expression. Like if I care about -1, near -1, this is just the function negative x, so I just work with that expression. Near, say, positive 13, this function is just x, so I just work with that expression. The only issue is when we hit a transitional point. In this case, the only transition is at 0. And I hope it's kind of clear what I mean by a transitional point. I mean a point where the definition, the defining expression in here changes. So at those points, what you want to do with piecewise defined functions is you look at the left and the right-hand limits separately, see if they agree, and whether the limit exists, and if it does exist, you compare it to the function itself. So it's actually really just a matter of checking those things. Does the left-hand limit exist? Does the right-hand limit exist? Do they agree? If so, the limit exists, and if that's true, then does the function exist and agree with the limit? And if all of the answers to those questions are yes, then it's continuous at the transitional point. If you get a no at any point in that procedure, then it cannot satisfy the definition of a continuous function at that point. Now, before we go on to talking about some more examples of piecewise defined functions, well, actually, let me just show you one more example just to kind of solidify the ideas of what we're saying here. So let's suppose that I want to know where is f of x equal to, let's say, 2x plus 1 for x less than or equal to 1, and then let's say that it is equal to x squared for x bigger than 1, continuous. Well, immediately right off the bat, I can say, okay, each of these expressions is a polynomial. So anywhere that in an interval around that point, it's given by just one of these expressions, it's going to be continuous. So we can say immediately it is continuous from minus infinity to positive 1, unioned with 1 up to infinity. The only issue is going to be at 1 itself. What happens as we approach 1? Well, as we approach 1, f of 1 is defined. It is equal to 2 times 1 plus 1, which is 3. The limit as x approaches 1 from the left, this is equal to the limit as x approaches 1 from the left of 2x plus 1, which is equal to 3. Okay, so far so good. The limit as x approaches 1 from the right of f of x, well, this is actually, I'm sorry, I'm probably blocking things, or at least putting a shadow on them, so this is difficult to see. The limit as x approaches 1 from the right, now I need to use the x squared definition. So I have the limit as x approaches 1 from the right of x squared. That's actually equal to 1. Now these are not equal to each other, so the limit as x approaches 1, f of x, does not exist, and therefore f is not continuous at 1. Okay, so what we've shown then is that it is only continuous on this part of its domain. And what this really is encapsulating here is the fact that we have a jump at this point. If you think intuitively of what continuous means, you would kind of think, well, continuous means something like we can kind of draw it without ever lifting our pen off the paper. And so if you have a jump, that should mean that it's not continuous. Yeah, that's exactly what this is showing us. We had a jump and it's not continuous. Now we want to talk a little bit about the laws for continuity, because there's some nice properties of continuity that we can get here. And they are the following. So let's suppose that f and g are both continuous at x equals c. And we want to talk about what kind of combinations of these are going to also be continuous. Well, then f of c exists, g of c exists, the limit as x approaches c of f of x exists, and let's say that this is equal to LF, and the limit as x approaches c of g of x, which we'll call LG, this also exists. So what we can say then is, what about the combinations of these things? Well, then what we can say is that f plus g evaluated at c, this is f of c plus g of c. Oh, and the other thing that we can say is that LF is actually f of c, and LG is actually g of c. Sorry, that's very important. I kind of dropped that for a moment, but that really is a crucial part of the definition of them being continuous. F plus g of c, though, is equal to f of c plus g of c, which is actually equal to the f limit plus the g limit, LF plus LG. Also, the limit as x approaches c of f plus g of x, well, this is equal to the limit as x approaches c, f of x, plus limit as x approaches c, g of x, which is LF plus LG. The limit exists, the function exists, and they both came out to the same number. That means that f plus g is continuous at c. Okay, so that is a nice result. We can now say if I have two continuous functions, then their sum is also continuous. Remember, I guess to be precise, what we want to say is if I have two functions that are both continuous at some point or on some interval, then their sum is also continuous at that point or on that interval. Now, we do need to be careful because you cannot go the other direction. You cannot say that just because f plus g is continuous, that does not necessarily mean that f and g themselves are continuous. And to see this, just consider for a moment, what if f and g were the same function? And what if they're not continuous? So they are not continuous, or rather I should say, what if g is negative f? Then f plus g would be 0 and continuous everywhere, whether f is continuous or not. So you got to be careful. If you have f and g continuous, their sum is continuous. But a sum being continuous doesn't tell us anything about f plus g. So just keep that in mind. Now, by a similar kind of argument, we can prove several other limit or continuity laws. Each one of them is going to follow from the rules for limits. So what we can say is f minus g is continuous at c, f times g is continuous at c, and f over g is continuous at c if g of c is not equal to 0. In other words, if this is defined at c. So if you have two continuous functions, then combining them using the basic arithmetic operations, the basic 4, that will always be continuous. At least as long as you're not trying to divide by 0. That's kind of the caveat here. We have to make an exception if you accidentally are trying to divide by 0. Or maybe not even accidentally, but if that happens, then, well, that changes things. So, one of the things that we can say from this is that a lot of the functions that we are familiar with, they are continuous on their entire domains, because most functions that we are familiar with are built out of what? Polynomials, exponentials, logarithms, and trig functions. If I do an arithmetic combination of those things, well, I get a combo that comes out to be essentially also continuous. Now, there's one more question here that we want to answer, and that is what happens with continuity under function composition. So what if I do f composed with g? Remember, f composed with g of x, this is f of g of x. Go back and review the stuff we talked about in week 1 about functions if you're having trouble remembering about composition. So what can we say about continuity in this case? What conditions do I need on f and g in order to ensure that this is continuous at c? Well, the answer is the following. Essentially, what I need is for g to be continuous at c and for f to be continuous at g of c. So let's write that down and see kind of why that is true. If g is continuous at x equals c and f is continuous at x equals g of c, then f composed with g is continuous at c. Why would this be true? Well, the idea is that if I want to take the limit as x approaches c of f composed with g of x, this is actually a bit of a tricky thing. What I need to do in order to do this is I'm essentially trying to ask, well, what happens as we go through this procedure? But if these limits exist and everything is continuous, then this comes out to be equal to f evaluated at the limit of g as x approaches c, which means it's just f evaluated at g of c, assuming that everything is continuous. So once again, this is one of those things that if we were doing an analysis course, I would definitely show you all the details. Since we're not doing an advanced analysis course, I'm going to kind of gloss over this and leave it for, if you're interested in it, please let me know, because I'm happy to talk about it further, but I think that maybe seeing all the technical details is not really necessary here. So this is how we can, this is another nice property, because this really tells us everything we do with the usual functions, at least all the normal things we do with the normal functions that we work with from pre-calculus is going to be continuous, unless we do something funny like we do a piecewise defined function with some jumps in it. Now, I do want to mention one other couple of notions of continuity that are somewhat important here. So another notion of continuity is we can say that f is continuous at x equals c if f of c exists and for any epsilon bigger than 0, there is a delta such that when the absolute value of x minus a, or x minus c, because I'm using c now, is less than delta, the absolute value of f of x minus f of c is less than epsilon. So it's very similar to the definition of the limit, except this time I'm not doing the 0 less than bit. I'm actually including what happens at c among the possibilities here. And so that is really important. Because I'm not ruling out that case, I'm actually able to say, well, yeah, this brings everything. Actually, I guess you could technically put in that 0 less than, but you don't need to in this case. If you did, it would imply this anyway because f of c exists. And actually, no, that's not true. You do need to have the 0 left out. Yeah, I take that back. This is exactly what we need. Because we need to make sure that this also holds when x is actually equal to c in this case. So this is sort of an alternative characterization of being continuous. And whether that's very useful or not, it kind of depends, but it can be kind of useful in certain situations. Now, another definition of continuity that can be somewhat useful in some situations is we can say that f is continuous on an open interval from a to b, so at all of these points, if the preimage of any open interval in the range is open. So what is a preimage? Well, a preimage just means all of the points that f takes into that interval. And so it's everything that gets sent into that interval. And so if every one of the preimages of open intervals is open, then it turns out that the function itself is continuous. And this is a nice characterization because it doesn't involve epsilons and deltas explicitly. there are two main advantages to this. One of the advantages is it doesn't involve epsilons and deltas explicitly, and so for some purposes, this can be somewhat easier to deal with. The other advantage is that later on in mathematics, you sometimes want to generalize the notion of continuity to situations in which differences like this cannot be explicitly defined. We don't necessarily have a notion of that, but we do have a notion of open sets. And so being able to characterize continuity just in terms of open intervals or open sets can be useful for generalizing continuity to other types of functions than just functions that take real numbers to real numbers. Now, I'm not going to bother showing you exactly why these two things are equivalent today, but I thought that I would mention this briefly. So let's go back to thinking about some examples involving continuity, and maybe some examples involving continuity and piecewise defined functions. So let's suppose that I have the function, or I want to know where is f of x equal to, let's say, sine x for x less than 0, and then it's going to be equal to 3x for x for 0 less than or equal to x less than 4, and then it's going to be equal to, let's say, 2x squared for x bigger than or equal to 4. So this is a piecewise defined function, and each of these pieces, each one of these, is continuous on its domain. So actually, I don't need to worry about checking within each of these, like within the interiors of each of these portions. I don't have to worry about it. The only places where we could get into a problem are going to be at the transitional points. Also, I'm not dividing by anything, so if I had any division by something, then I have to worry about maybe whether something is not defined or whatever outside of the domain. But this is going to be automatically continuous on minus infinity up to 0, up together with 0 up to 4, together with 4 to infinity. The only question is what happens at 0 and what happens at 4. Well, at 0, the limit as x approaches 0 from the left of f of x is the limit as x approaches 0 from the left of sine x. That is just sine of 0, which is 0. The limit as x approaches 0 from the right of f of x, this is going to be the same as the limit as x approaches 0 from the right of 3x. That's 3 times 0, which is still 0. And also, f of 0 is 3 times 0, which is 0. So all of these exist, and they are the same number. Therefore, the limit exists because the left and the right-hand limits exist, and they agree. And it's equal to the function at that point. So because the limit exists, the limit as x approaches 0 of f of x is equal to 0. It exists, and it's equal to the function there. Therefore, we are continuous at 0. Take a moment to make sure you've got all this written down. Even pause this if you need to, because I need to erase this so that we can deal with the case at 4. In fact, maybe try doing the case at 4 yourself before you watch what I do with it. So we've now found that we're actually continuous from minus infinity up to 4, unioned with 4 to infinity. Sorry, this does not look much like 4. But what we don't necessarily know is what happens at 4. Well, at 4, the limit as x approaches 4 from the left of f of x, this is going to be given by the limit as x approaches 4 from the left of 3x, and that is going to be equal to 12. Whereas the limit as x approaches 4 from the right of f of x, this is going to be equal to the limit as x approaches 4 from the right of 2x squared. And that is going to be 4 squared is 16 times 2 is 32. These are not equal, so the limit does not exist. Because the limit does not exist, this function cannot be continuous at this point. That means that we are not continuous at 4, so the set on which we are continuous is just all real numbers except 4. In interval notation, I can write that this way, but if I wanted to, I could also write all x such that x is not equal to 4. And there we go. We have proved, or we have figured out, calculated where this thing is continuous and where it's not continuous. So this is the basic thing that you're going to do anytime you deal with a piecewise defined function. You just consider each piece separately, and then you consider whether the function is, what happens at the transitional points, okay? Let me just do one more quick example here to show you something interesting that can happen. And let me make sure that this interesting thing that I show you actually sort of works out. So where is g of x, which is going to be equal to, let's suppose that this is equal to x squared plus 4x plus 3 divided by x plus 3 when x is not equal to negative 3. And then let's suppose that this is equal to negative 2 at x equals negative 3, continuous. Well, the answer to this is it's definitely continuous, except possibly at x equals negative 3. That is the only place I need to check. Everything else is automatic. Because except at negative 3, we are just a rational function that doesn't have a 0 in the denominator. So the only problem could occur at x equals negative 3. Now, the limit as x approaches negative 3, g of x, this is equal to the limit as x approaches negative 3 of x squared plus 4x plus 3 over x plus 3. That is the limit as x approaches negative 3 of x plus 3 times x plus 1 divided by x plus 3. X plus 3's cancel, and it leaves me with, if I plug in negative 3, I get negative 3 plus 1, which is negative 2. So the limit exists, and it's equal to negative 2, which is also what the function is equal to. Because the limit exists and it's equal to the function, which also exists at that point, this is actually continuous on all real numbers. Now, the interesting thing about this, the reason why I find this interesting, or why I think this is an interesting example, well, there's a variety of reasons. This is a little different than some of the examples we looked at before. But another reason that this is interesting is because think about what would happen if I just took this function x squared plus 4x plus 3 over x plus 3. If I graphed this thing, I would get what looks like this nice curve, except it would have a hole in it at x equals negative 3. But the fact is, we can fill in that hole to create a continuous function. So what we can actually sort of say here is that g of x is a continuous extension of x squared plus 4x plus 3 divided by x plus 3. What do we mean by an extension? An extension of a function is a function that is equal to our original function on its domain, but it has a new, larger domain. And in this case, Now, you can always expand the domain of a function by just defining it to be whatever you want at some new points. If my domain isn't all real numbers, I can always just start throwing things in at random. But we don't usually want to just throw things in at random because it's not useful. What we want to do is we want to make sure that our extension of a function has some useful properties. And in this case, the useful property that we can get is we can make it an extension that becomes a continuous function. And we do that by defining this to be -2 at x equals -3. The other thing to notice is that actually, in this particular case, g of x is just always equal to x plus 1. Like, that's literally all it is, because it's equal to x plus 1, except at x equals -3, but it's also equal to x plus 1 at -3. So in this case, they're just always equal to each other. And so, in fact, if you follow the same kind of argument, when you take a rational function and you cancel a common factor, what you are really doing, and you've probably done this in your pre-calculus when you try to make graphs, what you're really doing is you are creating a continuous extension of your rational function. So you take your rational function and you extend it to a new function that agrees on the domain, but it fills in some gaps. And it does it in a way that the new function is continuous, at least on its domain. Now, one of the things we're going to want to do, and this is very important because remember, one of our questions, one of the reasons we started thinking about limits was because we wanted to talk about this question. What happens to the average rate of change, f of b minus f of a over b minus a, as b gets closer and closer to a? Our question is, does this have a continuous extension to b being equal to a? In other words, I can think of this as a function of b. I fix the point a and allow b to be a variable, and then this whole expression becomes a function of b that is well defined as long as b is not equal to a, and as long as the function is defined, of course. But it's not defined when b is equal to a. Now, this expression is really the secant slope, or the average rate of change of the function. So what we can ask is, does the average rate of change of the function have a continuous extension to the case where we're actually just looking at a single point? Another way of thinking about this is, as we look at some curve, here's my A, and then as B comes in, I get a bunch of different secant lines here, depending upon where B is. But is there one specific slope that would sort of complete the family of secant lines so that their slopes form a nice continuous function as we move along this curve? If such a thing exists, then it would make sense to say that is the instantaneous rate of change of the function, or that is the slope of the function at this point. And that is precisely what we're going to do next week. In fact, this idea is really what is known in calculus as the derivative. However, before we get to that, there are a couple more properties of limits and continuity that we're going to want to talk about. So this lecture has gone on long enough, I think. We're going to stop this here, and I'll cover that in the next one.